Okay, let's continue. So the next part is approximation. Well, this basically uh, a summation that does not produce any closed form solution, and there are many such summation. Let's let's look. I will just skip this. I'm going to go right away to the summation. I mean, you can read it yourself. Yeah, you can read this motivation basically yourself. I'm going to continue right away to the uh, to the summation that we're going to see. This summation is called the harmonic number. The harmonic number, the nth harmonic number. So Hn is called the nth harmonic number, and this is uh, defined by the summation of I is equal to 1 until n, 1 divided by I. So the index is in the denominator. Yeah. So the index is in the denominator. So let's see, for example, a couple of examples. H1, when n is equal to 1, then this will be just the summation of 1 divided by 1. So this is equal to 1. What about when n is equal to 2? When n is equal to 2, there are two components. There are two terms right now. I is equal to 1 and I is equal to 2. So 1 plus 1 half, 3 and a half. H3 is 1 plus 1 half plus 1 third, 11 sixth. And then H4 is 1 plus half plus 1 third plus 1 fourth. Is equal to 25 12th. Yeah. Now there is no closed form solution of this one. You can try it yourself. Yeah, but there is no closed form solution for this one. So if there is no closed form solution for this one, how do we do it? So how do we approximate it? Well, one way to approximate this is by using the so-called the integral method. And this is important for you. An integral method is something really important, because anytime you find a summation and you don't know how to compute this, the only way to approximate it is by using the approximation, the integral method. So pay attention to this integral method. Yeah. So how do we do that? Well, if you see our function here, what we sum, you denote this as a function. 1 divided by I, you denote this as a function. Yeah, you denote this as a function. So this basically just says that Hn is equal to the summation of I is equal to 1 until n fi. Well, f is a function. What is fi then? Fi is equal to 1 divided by I. So treat this as a function. Okay. Now, if you treat this as a function, then you can actually draw them. You can draw them. Yeah. The first one, how do we draw this? Well, draw this in the discretized way first. Look at this function, 1 divided by x, 1 divided by x. When x is equal to 1, so in this region here, the value is equal to 1. When x is equal to 2, the value is half. So basically, if you see this well, this is another square. What do you call this? Well, you see this area here. This area has one area. Yeah. So this half. So the area of this basically is equal to half. What about this one? This is equal to 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, and so forth. Okay. Now, and then if you look at the function of 1 divided by x, 1 divided by x, this is the curve that is produced by 1 divided by x. 1 divided by x. This is the curve that is produced by 1 divided by x plus 1. 1 divided by x plus 1. Look at this, 1 divided by x plus 1. This is 1 divided by x, and this is 1 divided by x plus 1. Because what we are actually computing is those that are discretized here. It is easy to see that the area that we are looking for lies between these two curves. Yeah? So between is larger than below the curve 1 divided by x plus 1, but smaller than the area below the curve of 1 divided by x. Because of this, the only thing that we have to do is just to use integral. So this is the integral. Look at the first one. The first one is this one. Hn, namely those that are below these discretized areas here, must be smaller than this one. Yeah? Smaller than this one. Because this one, the area below this one is larger. Smaller than 1. What is 1? 1 is here, plus the integral from 1 until n. You start from here, you don't start from 0, you start from here. Start from 1 until n. 1 divided by x. Look at this. This is a curve. The curve here has a function. The function is 1 divided by x dx. What is the solution of this one? Well, according to calculus, the solution of this one is 1 plus the natural logarithm of n. Okay, this is one part. The second part is Hn, namely this one, is larger actually. It's not smaller, larger than this curve. This curve here has a function 1 divided by x plus 1. So if you see, Hn is larger than the integral from 0 until n. Look at this. Why do we start from 0 until n while here starting from 1 until n? Well, we start here from 1 until n because we don't compute this. That's why we go directly to 1, because the area below here is equal to 1. So we start from 1 until n, while here, second curve here, you start from 0. The area, so the integral from 0 until n, 1 divided by x plus 1. Look at this function. The function is no longer 1 divided by x, but right now is 1 divided by x plus 1 dx. And if you compute this integral, the integral will be the natural logarithm of n plus 1. So according to this one, this is our conclusion. Yeah, this is our conclusion. And our conclusion is the left hand side is this one, the right hand side is this one. The natural logarithm of n plus 1 is less or equal to Hn, less or equal to 1 plus the natural logarithm of n. Yeah, so that's it. So you know right now basically how to approximate this one. Our goal is to approximate this Hn, and this result basically tells us that it must lie between this one and this one. So this is basically the approximation. Okay, let me generalize this one. Yeah, let me generalize this one. If you have a function let's say that your function is fx. This is basically the function that you have when you have these the summation. So summation of something. So fx can be very simple. It can be, for example, is equal to x, can be x squared plus 1 and so forth. Any function whatsoever. Yeah, any function whatsoever. So what you have here, basically, wait a minute, I don't have any. So let me return again to this one. Oh, it doesn't really matter. This one is it's okay. So let me return again to this one. So assume that what you are being asked is not this function. This is a function. Fi here is equal to 1 divided by I, but something else, another Fi. So what is actually the final result? Yeah? What is actually the final result? So let's continue. Can you see my screen right now?
Yes, sir.
Yeah. Okay. So assume that you want to find any summation. So the summation has this particular form. The sum of I is equal to 1 until n fi. Fi can be anything. In our example, in our previous example, fi is equal to 1 divided by I. Then this is the formula that you're going to use. Then this summation will be less or equal to the integral from 0 until n fx plus I plus 1 dx, and it's larger or equal to the integral from 0 until n fx dx. But there is a catch. Namely, this is only when fi is increasing. What does it mean fi is increasing? So when you move from I, and then as I getting larger, then this function getting larger. When I is getting larger, then this function also gets larger. Now, if it is the other way around, namely when I is getting larger, then it is decreasing, then this is the formula that you have to use. And this, which is the case, will this basically just switch it. Yeah? So this, the summation from I is equal to 1 until n fi is less or equal to the integral from 0 until n fx dx. Look at this. So we just have to switch this. And this is larger than fx plus 1 dx. This one is for the case when fi is decreasing. What does it mean by fi is decreasing? Well, when I is increasing, fi decreases. Okay, so this is basically the general formula that you are going to use. So in our example, in our previous example, what we have been using is this one, the second one here. Yeah, because what? Because if you see, fi is actually decreasing. When I gets larger, for example, I is equal to 4, then the function fi is equal to 1 divided by 4. When I is equal to 2, fi is equal to 1 divided by 2. So it is fi is getting smaller, getting smaller, getting smaller, getting smaller. Okay, I hope that it is clear about the approximation. So that's it basically. That's how we use the what do you call this, the integral method. Let me return again. If it is not clear to you right now, just please ask me. Yeah, and I will tell you again about this one. But it is not actually important for you to draw this curve, for example. It is more important to look at the formula that I have just shown you and to use that. Of course, you have to compute it by using the integral. Yeah, so this is the final result. So what we know so far right now is that Hn, this is the one the harmonic number. This is the one that we want to find out is less or equal to 1, the less or equal to 1 plus logarithm, the natural logarithm of n. Yeah, this is by using the integral method, we know this. But actually, there is a more exact approximation, and this is given by this. Look at this. This is not even an approximation. This is equal here. This is equal here. We call this. This is a better approximation of hn. Is hn is equal to the natural logarithm of n. Look at this. Natural logarithm of n plus uh, plus gamma plus 1 divided by 2n plus 1 divided by 12 n squared plus epsilon n. Now, this is the catch. Epsilon n is a function. What is the function? We don't really know. We don't really know this function, but this function is somewhere between 1 and 0, divided by 120n to the power of 4. Now, if you look at this, and gamma here, which is called an Euler constanta, which is constants, which is around 0.577 and so forth. Now, that means that the harmonic number is something here, the natural logarithm, plus this one. Let's look at the rest here. This one is a constant. That means that this is not getting larger, this is not getting smaller, this is stay constant. But this one, what about this one? When n gets larger, this gets smaller. When n gets larger, this gets smaller. When n gets larger, this gets smaller. That means that when n gets larger, this stays the same. This is smaller, this is smaller, this is smaller. What does it mean? When n gets larger, actually, the harmonic number here, it's getting closer and closer to this one. You see the point? Yeah? So that means that when n gets larger, natural logarithm, it is becoming closer and closer to natural logarithm of n. Getting closer and closer when the n gets larger is shown to you by using this notation here. Notation hn approaches the natural logarithm of n is used to show that this one, the main term of hn is equal to the natural logarithm of this one. And we have the definition. For two functions f and g, we call f asymptotically equal. They are not actually equal, but they are called asymptotically equal. What does it mean by asymptotically equal? When the parameter gets larger, they becomes closer. So these two functions becomes closer and closer and closer. So we call this fx is asymptotically equal to gx. When what? When the limit of x to the approaching infinity, fx divided by gx is equal to 1. What does it mean fx divided by gx equal to 1? Well, this is just equal to gx here multiplied it with 1. So this is just the same as saying the limit of x approaching infinity, fx is equal to gx. So they get closer and closer and closer when x becomes larger and larger and larger. Yeah? So the first function that we know that uses this asymptotic notation, asymptotically equal, we call this asymptotically equal, is the harmonic number and the natural logarithm of n. Okay. Okay, let me continue. We don't have much time anymore, actually. We're going to finish by 1 o'clock, and there are still many things that we have to cover. Well, if we cannot cover it, then that's okay. You can read it yourself. Basically, I will not try to finish it next week. Next week, I will go to the next chapter because we don't have much time. Now let's continue. Another use of integral method is not actually just for approximation. You can also use integral method to find the closed form solution. This is the beauty of it. So for example, where do you get the closed form solution actually? The closed form solution is usually obtained by trial and error, by testing them, by looking at how to use them. For example, let me ask you this one. What is the summation of I is equal to 1 until n I squared. Look at this. This is the other thing that I mentioned before. So if the index is on the power, then you use the geometric sum. But if the index is not the power, this one, we call this the summation polynomial. So the index to the power of something. So this is completely different. You cannot use geometric sum for this one. But the problem is, what is the closed form solution of this one? How do we answer this? Well, one way to answer this is by using the integral method. The integral method. So how do we do this? Look at this. Like I said before, I've already shown you the formula. So this is our function. Our function here, fi. Fi is equal to I squared. So the summation of I is equal to 1 until n I squared. According to the formula that I have given you, the first thing is, what about this function? Is it decreasing or increasing? What about this function? Anyone? Anyone? Anyone can hear me? So look at the function again. Yeah, this function here, the function is fi is equal to I squared. What about this fi? Is it decreasing or increasing? Yeah, well, it isn't increasing. For example, if you say I is equal to 1, when I is equal to 1, then I squared is equal to 1. When I is equal to 2, then I squared will be 4. So you see, it is decreasing. When I gets larger, then the function gets even much larger. Because it is increasing, then this is the formula. You always take this. Look at this. This is x plus 1 to the power of 2. This is not x to the power of 2 plus 1. This is x plus 1. So the x1, fi. So fx plus 1. So if fx is equal to x squared, then fx plus 1 is equal to x plus 1 to the power of 2. So this must be smaller than the integral from 0 until n x plus 1 to the power of 2, and larger than the integral from 0 until n x to the power of 2. And the only thing left for you to do is to find the integral. And this is the integral. The integral is n plus 1 to the power of 3 divided by 3 minus 1 divided by 3. What can we infer from this one? Well, based on this approximation, this is just an approximation. But if you look at this approximation, it's actually quite easy to see that, yeah, that this is that the sum from I is equal to 1 until n I squared is asymptotically equal to, look at this, asymptotically equal to n to the power of 3 divided by 3. Yeah. So if you look at this also, if you compute this, you will find later on that this will be n to the power of 3 divided by 3 plus something else. So the main term there, the largest term is n to the power of 3 divided by 3. So you have an idea right now that I don't really know exactly what is the result of this summation, but it must be of the form n to the power of 3 divided by 3. Yeah? So you use this fact. Yeah? So because this is n to the power of 3 here, the main term is n to the power of 3, so you say that this is a cubic function. So even though you don't know the exact way, but you know that the exact way will be just like this one. A, because this is a cubic function. A multiplied by n to the power of 3 plus B multiplied by n to the power of 2 is a cubic function. This is the general cubic function plus C to the power of multiplied by n plus D. I don't know D, I don't know C, I don't know B, I don't know A. But no matter how they are, the form of this function, the closed form solution of this one must be of this form. I don't know the detail. Yeah, it is just that I don't know the detail. So how do I know the detail? By trying a couple of values. You can try a couple of values. How do I try a couple of values? Let's see, for example, let's start from n is equal to 0. When n is equal to 0 here, yeah, when n is equal to 0, then you see n is equal to 0. It is easy. Just fix here n is equal to 0, then this one will be equal to 0. Yeah, the summation from I is equal to 1 until 0, I squared, this will be just equal to 0, because the boundary here is smaller than the lower boundary. What about on the right side? On the right side, just put here n is equal to 0. When this is equal to 0, then A multiplied by 0, B multiplied by 0, C multiplied by 0, plus D. On the left hand side, this is 0. So 0 is equal to D. Easy. So it's right from the start, we know that D must be equal to 0. D must be equal to 0. Okay. Let's try the next one. N is equal to 1. N is equal to 1. So I is equal to 1 until 1. So, and then I to the power of 2. So 1 to the power of 2. So this is equal to 1. The left hand side is equal to 1. What about the right hand side? The right hand side is easy. A multiplied by n, n is equal to 1, 1 to the power of 3. So this is A, B, n to the power of 2, 1 to the power of 2 is equal to 1 also. And this also, so you see, 1 is equal to A plus B plus C plus D. Well, actually D, you don't really need this D anymore because you know that the D is equal to 0. Yeah? You try again n to the power n is equal to 2. When n is equal to 2, then this one is 1 to the power of 2 plus 2 to the power of 2, which is equal to 5. What about this one? This one will be A multiplied by 2 to the power of 3, 8, plus B multiplied by 2 to the power of 2, 4, plus C multiplied by 2. So you have this one. And for n is equal to 3, you have this one. So what do you have? In the end, you have a system of linear equation. Yeah? This is just a system of linear equation. This is just a system of linear equation. And you can solve this system of linear equation by Gauss-Jordan, by LU decomposition, by I don't know, Gaussian elimination and so forth, or by using matrix. Yeah, by using matrix. So if you look at this is basically this solution of we can actually denote them as this one. 1, 1, 1, 8, 4, 2. So 8, 4, 2, 27, 9, 3, and this one is a matrix multiplied by A, B, C, and this will be equal to what? 1, 5, 15. This will 14, 5. This is basically what we are just doing. Yeah. So this is a matrix. The first matrix. Yeah. And this is the factor. So if you multiply this by this one, this is the result. So and then the only thing that is left to do for you to do is to find ABC. What is ABC? You know how to deal with this. So the solution of this system of linear equation, the solution of this system of linear equation is equal to A equal to 1/3, B equal to 1/2, C equal to 1/6, and D is equal to 0. So the final result then is this one. So the summation of I is equal to 1 until n I squared will be equal to n to the power of 3 divided by 3 plus n to the power of 2 divided by 2 plus n to the power of 1 divided by 6. And this is equal to 2n plus 1 multiplied by n plus 1 multiplied by n divided by 6. You see? So the integral method is basically just used. Yeah, it is used for us to have an idea what is the polynomial that we use. What is the degree of the polynomial that we use? For this case, for example, you see that the degree of the polynomial that we use is equal to 3. And because a polynomial of degree 3 has this general solution, then you try it yourself. Yeah, you do trial. You try. You perform trial to look at what is the form of that. Okay, so well, there's a question here. Is there any other way, maybe from the upper and lower bound from the previous slide, to calculate it other than solving the linear equation? For the summation of the form of this polynomial form, there is no other way. So the final way is basically look at this the solution of the upper and lower bound and use it basically to generate a polynomial, and how do you get this parameter of this polynomial? Then the way for us to do it, the coefficient of the polynomial, we obtain this by by testing, by using a couple of values, by trying a couple of values. Now, do you have to use this particular value n is equal to 0, 1, 2, 3? No, it's up to you. Because here there are 4 unknowns, you need 4 equations. That means that you have to use 4 different configuration. But you can use other. You can use, for example, n is equal to 1, n is equal to 5, n is equal to 10, n is equal to 15. But if you use this larger n, of course, your equation here will be much more complex. So we usually try as simple as possible. Yeah? So is there any other question? If there is no other question, I will give you again another 1 minute another 1 minute rest basically, and then I will continue with the next. Okay, let's continue. Now what have we seen? We have seen a way to find the closed form solution. If the index is on the power, you have to use the geometric sum. If the index is something that is powered, you can try to use the integral method to find the closed form solution. We have also seen the approximation. Yeah? How do we perform approximation? Use the integral method. And for the integral method, I've already shown you also the formula, the general formula to find. Okay. Now let's continue. I don't really think that we will be able to go to the end of this chapter, but there's something that is really important that I have to cover, namely it is called double sums. What does it mean by double sum? Double sum is summation that is doubled. Sometimes there are many occasions that you need this. So the summation is just, it's not just one single sum, but a couple of sums. Yeah. Sometimes we need to evaluate summation of a summation. Summation of summation. This is what we call a double sum. Of course, this can be also triple sums. Yeah, 3 times, 4 times, 5 times, and so forth. But uh, uh, in general terms, you can also always see them as a double sum. So how do we solve this? The first method is like this. Look at the inner sum. The inner sum is the one that is inside. Look at the inner sum. For example, let me show you a double sum. This is a double sum. Yeah, this is a double sum. Now in this double sum, this one here, this sum here, we call this inner sum. While this sum here is called the outer sum. Yeah. So this first method is evaluate the inner sum. If you can evaluate the inner sum and it has a closed form solution, then everything perfectly fine. Everything is perfectly fine. So this basically means that if you have this one and this has as a closed form solution, then replace this by the closed form solution and then do again. So you basically just you just succeeded in eliminating one sum. So the only thing that is left for you to do is to perform the next summation, and again the next summation, the next summation, and the next summation, and so forth. Yeah. So if you are able to find the closed form solution, then the thing becomes really simple. But sometimes this is not possible, especially if we cannot find the closed form solution of the inner sum. Yeah. So if this happens to you, what do you have to do? Well, what you have to do is look at this. Sometimes it is worth trying to exchange the order of the summation. Try to exchange the order of the summation. If you exchange the order of the summation, then sometimes you find a way to find the closed form solution and a better way to express your sum. But exchanging the order of the summation requires understanding. You have to really understand the summation. If you don't understand the summation, then the whole thing becomes jumbled. You have to be careful about this. And then I'm going to show you how to do this. Yeah? I'm going to show you how to do this. Let's see an example. We are going to use this as an example. This is basically the summation of the n, n first harmonic number. This is a harmonic number, hk is a harmonic number, and you sum the first n harmonic number. So you have this summation. The summation of k is equal to 1 until n. The summation of j is equal to 1 until k, 1 divided by j. Look at this summation. This is the inner sum. This is the outer sum. What if you go to the first method? Well, the first method is this one. This, like we have seen before, has no closed form solution. This does not have a closed form solution. It has an approximation. Yeah, this one has an approximation, namely the natural logarithm of n. But we cannot use that. Yeah, we cannot use it. You have to find a closed form solution. Now, if this is the case, sometimes it is worth trying to exchange the order of this sum. But you have to understand the order of this sum. What does it mean? Well, let's look at this table. Let's look at this table. This is when I vary j. So when j is equal to 1, 2, 3, 4, 5. So this column basically means that j is varied from 1 until n. Yeah? So this is j. But you say j is not from 1 until n, but j is from 1 until k. It doesn't matter. Yeah? Now, again, on this side, on this, the rows of this table, the rows of this matrix, I list k, and k here, yeah, proceeds from 1 until n. So 1, 2, 3, 4, 5, and so forth. Now, what we are going to do is to fill the entries inside of this matrix. How do we fill this matrix? Well, we fill this matrix by trying this particular formula. Let's look. When k is equal to 1, when k is equal to 1, look at this. When k is equal to 1, yeah, when k is equal to 1, then j can only be from 1 until 1. And because j can only has value 1, then this value here is 1 divided by j, 1 divided by 1, 1. So when k is equal to 1, j is equal to 1, the only value is equal to 1. When k is equal to 1, it is not possible for j to have value 2. It is not possible because j is something from 1 until k. So this is 0. So we don't have to fill all of this one. Okay, let's see the next one. When k is equal to 2, what happened? When k is equal to 2, then j can be 1 and can be 2. When j is equal to 1, then this value, this function here, 1 divided by j is equal to 1. When j is equal to 2, then the function is equal to 1/2. Okay, let's continue with this. When k is equal to 3, then j can have value 1, 2, 3. When j is equal to 1, this value here is equal to 1. When j is equal to 2, 1/2, this is 1/3, and so forth, and you see the pattern. Yeah? And you see the pattern of this formula here. Now, look back again on this matrix. What is it actually we are doing when we perform this summation here? When we perform this summation, what we do is actually we sum these columns here. So when j is equal to 1 until k, when k is equal to 1, so you sum this all. What is the sum of this one? 1 is equal to 1. Yeah? What is the sum of this one? This is equal to 3. Yeah? This is this is equal to 3, 1.5. This is 1.5. You sum them 1.5. What about this one? You sum this all and you sum this here. You sum this here and so forth. Yeah? So in the end, when you perform this second sum here, what you do is to sum this from from the top down. I think it is better if I use an Excel to show you this one. Let me show you this one. Okay. Now, remember that J is on the columns. So, and then here is K. K can have value 1, 2, 3, 4, 5, and so forth until n. Now, what about J? When J can also have value 1, 2, 3, 4, 5 until n. Yeah? Now, when j is equal to Now, when j is equal to 1, we have here 1. When k is equal to 2, j can have value 1 and 2. 1, this is 1 half. 1 half. This is 1. 1 half. 1 third. This is 1. This is again 1 half. 1 half. 1 third. Yeah. 1 fourth. This is 1. 1 half. 1 third. 1 fourth. This is 1 fifth, and so forth. Let's look at the last one. This one, 1n. 1, 1 half, 1 third, 1 fourth, 1 fifth. What about the last one here? Yeah, the last one here will be 1n. Okay, now what we do in the summation is we sum this one to the right. So this is basically the sum. The sum is 1. This is 3 divided by 2. This, how much is that? I don't know. You can try it yourself. Yeah. Well, yeah, 16, 11 sixth, and so forth. Yeah. 11 sixth, and so forth. Yeah. And you can read it. You can try this. And what about this one? I don't know. But then the second one, what you do is you sum after this. You sum all of them one by one, and then in the end you sum the whole thing here below. This is the second. This is the outer sum. So the inner sum basically performs summing these columns. This is what is being done by the inner sum, while the outer sum summing this last column here. Yeah, summing all of the rows in the last columns. Okay, now, but if you think about it, there is actually another way of looking at this table. Namely, why don't I sum per column first? Look at this. I can sum this all thing. 1, 1, 1, 1, 1, and there are n of them, so that means that I have here n. What about this one? This will be 1 half multiplied by n minus 1. Yeah? What about this one? Everything is 1 third. This will be 1 third multiplied by n minus 2. Why is it n minus 2? Because this one is empty. Why is it n minus 1? Because this one is empty. And you can see the pattern right now. The pattern is this is 1 fourth multiplied by n minus 3, and so forth. This one will be 1 fifth multiplied by n minus 4, and so forth. And the last one here, 1 n. So basically, what you do is to switch the order of the summation. When you switch it, then the next one is the only thing that we have to do is to sum this. From the left, this one, plus 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 this one. And we have here something here. This something, no matter what your order, if your order is summing the column first and then the rows here, or summing the rows first and then the columns, they're supposed to be the same. They cannot be different. Yeah, they cannot be different. So this is basically this is what I mean is you have to understand the sum. Now I'm going to continue with the slide. Yeah. So that means that I have just switched how we look at this. So this is the original one. Yeah. The summation of k plus 1, k is equal to 1 until n. Summation of j is equal to 1 until k, 1 divided by j. And it's become, look at this. You have to be able to understand this one. This one is the one, the order that I have mentioned to you before. So right now here, k is equal to j until n. What does it mean actually? K is equal to j until n. So this is the one. K, k is equal to j. K is equal to, for example, k is equal to j until n. K is equal to j until n. Yeah? K is equal to 4 until until n. This is basically what it means in this part here. Yeah? So what about this? J is equal to 1 until n. J is equal to 1 until n. Where j is equal to 1 until n is on the last part here. You go from j is equal to 1 until n. Now, let's look first about this one. About this one, this is easy. For k is equal to j until n, this is multiplied by 1. Yeah, this is multiplied by 1. Why is it multiplied by 1? Think about it. Yeah, and this is 1 divided by j, so we just have to move it inside. And you have to move it inside, and this becomes basically k is equal to j, the summation of k equal to j plus until n of 1. So this basically means that you start from j, j plus 1, j plus 2, j plus 3, and so forth until n. How many do you have? This n minus j plus 1. So the final result is equal to the summation of j is equal to 1 until n, 1 divided by j multiplied by n minus j plus 1. Let me return again to this Excel slide to show you a better way of doing this, a better way of looking at this. Yeah? So look at this. This is the one when it's n. So you know this n. This is 1/2 multiplied by n minus 1. Yeah. This is 1/3 multiplied by n minus 2. If we go back again to the slide, you will be able to see it. Take j is equal to 1. J is equal to 1. When j is equal to 1, this is 1 multiplied by n. J is equal to 1. This is 1. So minus 1 plus 1. So this is just n, according to the result. What about j is equal to 2? J is equal to 2 will be 1 divided by 2. What about this one? N minus 2 plus 1. So n minus 1. This is what we have seen before. And you sum this from j is equal to 1 until n. Okay? So what do we do? What do we do right now? Well, what you do is just, it's easy. This is n divided by j minus j divided by j plus 1 divided by j. So this is the result. Yeah. So j divided by j becomes 1. So the summation of n plus 1 divided by j here, yeah, minus the summation of j is equal to 1 until n, 1. N plus 1 can go to the front, n plus 1. The summation of j plus 1 until n, 1 divided by j minus, what about this one? It's easy. The summation of j is equal to 1 until n is just equal to n. So what about this one? We return to this one again. This is a harmonic number. There is nothing that we can do about this. It has no closed form solution, but we know this is a harmonic number. So the final result will be n plus 1 multiplied by the harmonic number minus n. And so you see, the trick of double sum is to understand how actually do we perform the summation and then change the order of the summation. So if I ask you about this during the exam, always bring it to the matrix form and try to understand it in the matrix form. Once you go to the matrix form, this will become easier. Okay, we don't have much time anymore. I'm going to continue a little bit more to solve the to finish this Stirling approximation. Yeah. Now let's go back again to the Stirling approximation. There is no closed form solution of Stirling approximation. We can just use approximation for this one. But again, I will demonstrate to you right now that we can always change product to summation. If you listen to me, then right from the very beginning, I always talk about summation, summation, summation. I never talk about product. Why is it the case? Well, this is the case because if you encounter a product, you can always change it into summation. How do I do that? Look at this. This is a product. N factorial is a product of I is equal to 1 until Ni. This is equal to 1 multiplied by 2 multiplied by 3 and so on multiplied by N minus 1 multiplied by N. Because these are all multiplication, we can change this into summation. By what? By using the property of the logarithm. So you see, if I ask you about something related to product, you can change this problem to summation just by using the logarithm. Take the logarithm of the left and the logarithm of the right, they must be the same. The natural logarithm. What about if you don't want to use the natural logarithm? You use other logarithm. They are just the same. But to be more convenient, we just use the natural logarithm. Natural logarithm of n factorial is equal to the natural logarithm of this multiplication. But the natural logarithm of multiplication is the summation of the logarithm. So this will be equal to logarithm of 1 plus logarithm of 2 plus logarithm of 3 and so forth until logarithm of n. So this will be equal to sum. You see, a product becomes a summation. The sum of I is equal to 1 until n, the natural logarithm of I. So you see, right from the beginning, I always talk about summation. It has actually an objective because once you are able to solve the summation, the product comes for free. Now, let's continue with this one. How do we go on with this one? Well, because this is approximation, we can go. We can do this. By what? By integral method. We can use integral method to do this. This is the integral method, basically. Yeah? Because this is an increasing function, then the sum of I is equal to 1 until n, the natural logarithm of I, is less or equal to the integral from 0 until n, natural logarithm of x plus 1. Look at this. And it's larger than the integral from 1 until n. Why is it from 1 until n? Because we see here, we start from 1 here. If you start here from 0, then it doesn't make sense because there is here a negative term. So it is starting. So you are supposed to be careful about these boundaries. 1 from n, 1 until n, natural logarithm of dx, natural logarithm of x dx. So you compute this, and this is the result. This is the result. This is the result. Yeah. Look at this. N, natural logarithm of n divided by e plus 1. The integral of this one is n plus 1. The natural logarithm of n plus 1 divided by e plus 1. But you have to remember, of course, that this is equal to natural logarithm of n factorial. So if what you want is n factorial, then this natural logarithm must be converted to a factorial. How do you do that? Well, this is just e to the power of this one. E to the power of this one will be e equal to e to the power of this one will be equal to e to the power of this one. Yeah, this is e to the power of this whole thing here becomes this one. How do I get this? This is easy. Inside of the logarithm, n divided by e. This is because e to the power of n, this becomes the power plus 1 multiplied by e. What about this one? This is n plus 1 divided by e to the power of n plus 1 multiplied by e. So you see, we have right now the approximation of factorials. Uh, but still, this is actually a very rough approximation. There is uh, someone called Stirling, and Stirling has this lemma. He could prove that n factorial is asymptotically equal to n divided by e multiplied by n to the power of n multiplied by 2 pi n, the square root of 2 pi n. Yeah, so that's it. Basically, I'm not going uh, to to comment much more about this one, but this one actually is really good. This is really close. Stirling's lemma is really close. This is a little bit different from our result here. Our result here, this is a standard by using integral method. This is pretty advanced. There are many things that we have to learn first to be able to prove this Stirling's lemma. So that's it. I will not be able